Hi, let's go through activity 2 and just check in on your answers to make sure that you are getting the right idea with some of the questions. Activity 2 is called current and voltage, and those are the two things that you were learning about with these slides. So in this first slide, this is slide 2 actually, you read about electric current. Let's just talk about some of the answers to the questions. Question 1, in terms of potential energy difference, why does water flow downhill? And the answer is that water always flows from high potential energy to low potential energy. Anything will roll downhill or move downhill or go lower because it's trying to go to a lower potential energy. Number 2, what conditions are needed for electric charge to move from one point to another? There must be a difference in potential energy or voltage between those points. Number 3, when do charges stop flowing? They stop flowing when there's no difference in potential energy. All right, or you could say there's no difference in the voltage between 2 points. Number 4, what actually moves in a circuit, electrons or protons? Electrons. Number 5, we call those electrons conduction electrons. And number 6, the unit that we use to measure the flow of electrical charge is called the ampere, and its abbreviation is a capital letter A. Number 7, if the wire carries a current of 10 amps, how many coulombs of charge will be moved in 5 seconds? Here's a way that you can solve that. 10 amps is equal to question mark coulombs, right? That's your unknown, divided by 5 seconds. And so then you can solve for that question mark, right? You can cross multiply both sides by 5. It turns out that that's 50. That's easy to check. You could take 50 and you could divide 50 by 5 seconds, right? Plug 50 in here. 50 divided by 5, that gives you 10 amps. Question 8 is a trick question. It says which current is greater. In fact, they are the same. And so you can show that by calculating the current. So 100 coulombs divided by 50 seconds is 2 amps, but so is 1 coulomb divided by 0.5 seconds. So current is basically, the rate of charge moving. So C's, the letter C stands for coulombs. Those are charges. Of course, S is for seconds, and A would be amps. Number 9 is the net charge in a wire, positive, negative, or neutral. It is neutral. So every circuit, every part of a circuit, every wire, every light bulb, every battery has the same number of positive and negative charges. So overall, they cancel out. That's neutral. And current is called a rate. Rate is how fast something happens, and so current is a measure of how fast the charges flow. Okay, let's move on. All right, that's a little bit better. On the next slide, you actually built a circuit, okay, and you used an ammeter to measure the current in the circuit at different places. And an ammeter measures amps. And I hope that you found that the current is exactly the same in all places in the circuit. And that goes back to stuff we talked about in class, because the charges all have to follow the same path. Okay? That's a very important concept. It's easy to show, right? If you complete the circuit and you put the ammeter in, I can hover, right? 0.9 amps in that wire, but it's the same any place in the circuit, even through the battery. And you can also see it if you watch my cursor as I move along. You can see how the rate or the speed of those charges does not change ever. So that's a really important idea. And there is a question here about conventional current at the bottom. And conventional current is basically going in the opposite direction. If you're wondering what conventional current is, it is the direction that positive charge would move, if positive charges could move. So it's the opposite of electron current. All right, so that was that. Some questions about voltage again. And looking at the answers here, you're going to see, like, number 1 is very important, that you need to have a voltage difference in order for charge to move or charge to flow, a difference. Okay, that means that the voltage has to be high in one place and low in another. Of course, that's what a battery does for you. It gives you that difference. The units are volts, right? The symbol is a V for volts. Like you might have a car battery that has 12 volts, or you could have an outlet in your house that has 110 volts. Another name for voltage is electric potential. People, we say that voltage is applied across a circuit, but current flows through a circuit. So those words are important, across and through. And the reading talks about batteries and generators, okay? By the way, that's a good little cartoon at the bottom here that explains, as this guy tilts the pipe, right, he creates a difference in potential energy, and the water is going to flow from the high end to the low end. Some questions here about roller coasters. This is there's nothing that you read about this. This was more about just can you make the connections. So I guess the main thing is if you look side by side, we'll do these questions. For question 1 and question 6, right? When you go from A to B on the roller coaster, your potential energy increases. When you go from A to B in a circuit, your potential energy increases. Now, number 2, on a roller coaster, the energy, where does it come from? Well, it comes from the electric motor that lifts the car. In a circuit, it comes from the battery. 3, potential energy from C to D and E to F, right, on a roller coaster. Those are places where the car is dropping down. And what happens is potential energy decreases. Question 8, going across, the exact same thing happens with electricity. The potential energy decreases as you go through the light bulbs, right? So C to D is like where the energy is kind of like it's turned into light and heat. And so that gets into our next question, number 4. In a roller coaster, the energy becomes kinetic energy of the car, but in a circuit, it becomes light and heat. And 5 and 10, the answer to both of those is no. Okay, so potential energy does not change on flat sections of the track. It doesn't change in the wire segments either. So 9 and 10 are both no. Okay, a couple things here about batteries. And if you change the direction of a battery, it does not change the brightness of the bulb. What it does do is it changes the direction that the current moves. And you'll notice that when you increase the voltage of the battery, the bulb gets brighter and the charges move faster. In this part, you had to actually use a voltmeter to measure voltages across different things. I didn't put the answers in here, but what you should have been measuring was probably 9 volts get used on the bulb, 0 volts on the wire, and 9 volts are provided by the battery. So basically, the battery creates this voltage difference of 9, and it all gets used on the bulb. So the voltages have the same size, right? That's something you should have noticed. And if you look at any wire, right, on the wire, there isn't any voltage difference at all. And I don't know if you can hear the electricity is happening outside right now as it's raining. It's kind of cool. All right. Some questions here about batteries. You can just test this out. But as you stack batteries head to tail, the voltages add up. There you go. If you put 4 batteries in series like this, head to tail, each one is 1.5. They add up to 6 volts. And the last slide here is just about different ways of connecting the batteries. And you have to just pay very close attention to head to tail. There are a few of these where they kind of get mixed up, right? See, case D, you see how those last 2 batteries are head to head? So these last 2 batteries, they cancel each other out. And all you're left with is the first 2 batteries, which brings you back to 18 volts. So you just have to pay attention to that. Also, F has some batteries that are head to head. Okay. So you could rank those. I guess you can check your work on this, but obviously you have to measure the voltages first, and then you can rank them. Notice that I'm putting unequal sign here or an equal sign. But that's the idea with that. All right, so the way to do this with the largest possible voltage difference is to go head to tail. Okay, so I'm now going to go through the blue slides at the end of activity 2. These slides are really just kind of meant to be a summary of the things that we've learned. And these are kind of some of the most important things. So the first slide talks about electric current, and it gives a definition. It says electric current measures the rate at which charges flow through any point in a circuit. Guys, if you have a high current, that means a lot of charges are passing through each second. So kind of like a definition in terms of like math. right? A formula, if you will, would be that current is equal to the amount of charge passing through the circuit divided by the time that it takes. Current is measured in units called amps. Okay, that's the letter A. Charge is measured in units called coulombs, and that symbol is C. So down at the bottom, there's an example of how you could use this. I know that you did this already on slide 2, but you could say that current is equal to 100 coulombs divided by 5 seconds. And so 100 divided by 5 is 20 amps. Okay, so that's an important thing. You should know that definition. You should understand it. You know, it's really like if you had a wire or something like this, and you could count these charges that are going by. Now, I'm going to put positives here, but let's just pretend that they're positive. I know that positives don't move, but so these currents are going by, and so you're standing here, right, and you're watching, and you're saying, well, how many of those things go by? So maybe each one of those is 1 coulomb, right? So maybe this is plus 1 coulomb, each one of those. So if I'm standing here and I'm watching, and I notice that maybe 8 of those coulombs go by, so plus 8 coulombs go past me, and maybe it takes, let's say that it takes 4 seconds. Well, that tells me something about how fast they're moving, right? So 8 coulombs pass me. They pass this dashed line in 4 seconds. So that would be 8 divided by 4 is 2. And we say that's 2 amps. Okay, so that's kind of that's what current is. So current is that type of a thing. Can you see also, like, let's say that I had twice as many charges passing. Let's say that I had 16 coulombs passing by, right? And they pass by maybe in, let's just say that it takes 32 seconds for that to happen. So more charge is going by, isn't it? Because 16 is bigger than 8. However, it takes a lot more seconds for that to happen. So this is going to be a low current. Okay, this should be slower. So 16 divided by 32, that's about 1/2. That is 1/2. So the currents are quite different. Even though the charges are different, the charges increase. The current actually goes down because it takes more time. Okay, so just be able to do that. One other thing that's useful with this formula is you can sometimes flip things around. Like, let's just go with this first example here. I'll draw it over here. So if I have 8 coulombs in 4 seconds, 8 divided by 4 is 2 amps, right? But what if it was worded a little bit differently? What if the question was, how many coulombs pass in 4 seconds if I have 2 amps of current, question mark, right? So how many coulombs would pass me in 4 seconds if the current was 2 amps? Now, did you see what you can do here? Is you can just take these numbers and you can kind of rearrange them. So I know the 4, right? I know the 2 amps. And I know that the answer must be 8, right? And I hope you can see that you can just rearrange the math up here, right? And you can say, well, 8 coulombs is equal to 2 amps times 4 seconds. And so that's how you can actually figure out the charge, okay, if you want to. Let me just give you another example that's a little bit less obvious, right? So let's say that, for example, the question is, how many coulombs pass in, how about 5 seconds if the current is, 4 amps. So that's your question, right? So just check with your partner, right? Can you figure that one out in your head? Think about the math. So again, the way that you find that out then is if you can take the current. I'll write this in words and then we'll do the math, right? But you can take current times time, and that's going to be equal to the charge. So I hope your answer was 20. So how did I get that? How did you get that? You took 4 amps times 5 seconds, multiplied by 5 seconds, right? So current times time is equal to charge. So 4 times 5, that's 20. And if you ever multiply amps times seconds, you get coulombs as an answer. So that's the kind of math you would do with this formula. Okay. All right. So that's that. Flip this around. And one other slide here about current. I know we already talked about this, but it's so important. We're going to emphasize it. We talked about how current is the same in all locations in a loop, right? We did see this, right? When you measure the current in a circuit, no matter where you put this ammeter, right, you always get the same current. So that's really important. And that is really telling you that electric charge cannot be created or destroyed, right? The total amount stays the same. So when you say something is conserved, that means it stays the same. Okay. And it is. It's because you're not. It's not like you have like 0.9 amps here and then 20 amps over here, right? Because how could that happen? That would have to mean that somehow you have more charges over here than on this side. And that doesn't happen with electricity. So that's an important thing. Okay, and then the last couple slides here are about voltage. Voltage is sometimes called potential, and voltage is a measure of how much energy charge has someplace in a circuit. The definition of voltage is that voltage is equal to the energy divided by the charge in a circuit. We're not going to use that formula really for too much in this class, but the main thing I want you to see is that voltage is related to energy. It's connected to energy, okay? And it's the energy that every charge carries with it. So voltage is measured in volts. So if you buy a battery that has, say, 12 volts of voltage, that's telling you something about how much energy every charge can carry. And I know you read about this, but charges naturally will flow, that is, be pushed from high to low voltages, just like water naturally flows from high to low elevations. Okay. We tried this out in the activity 2. Whatever energy the battery gives you, it gets transformed into heat and light in the bulb. So the idea would be that your energy is also conserved because the battery gives you energy, but then the bulb uses up the exact same amount. It transforms it into heat and light. So that's an important thing also. All right, and then last slide here is this is how you measure current and voltage in a circuit. We will be doing other circuits, of course, in the coming couple of weeks. And just remember, with a voltage meter like this, you always put the voltage meter on opposite sides of the thing you're trying to measure voltage across. So if I want to measure the voltage of the battery, I've got to put one of these, the black thing on this side and the red thing on the other side, or vice versa. Okay, but you have to put them on either side. You put them across to measure voltage. And with the ammeter, the ammeter basically just hovers over a part of a circuit, and it measures the current through that part of the circuit.